Energy is the ability to do work. And when you first see this definition, you go, okay, that's a kind of an interesting definition. I'm not sure what work is, and I'm not sure what energy is. You may be familiar with energy from chemistry class, but as far as physics goes, you're going, okay, I'm not so sure about that. But this really packs a really good definition that's there. So let's think about what we talk about when we want to do work. So work is this idea of being able to do something mechanical. So a lot of us are familiar. I've got a waterfall here and I have a water wheel. And I've got my water wheel turning, and as the water comes over, and I'm going to be able to rotate my water wheel, and my water wheel is going to rotate a shaft, and I can have that shaft do milling. I can have that shaft do grinding. I can have that shaft do a variety of different things. But this water that's coming through here, it's going to be kind of interesting because it's at a height h, and as it comes down the waterfall, it falls down. And one of the things that we know is if I drop something here, my initial velocity is 0, and down here I'm going to have some final velocity. So we get some interesting things that are going on, and I get a drop here, and I've got gravity. So if I store a rock at a height, like I've done this with my water well, or if I've done let's think about a well and a bucket. If I've got a well and I've got my bucket here, and I've got this bucket, and we can have it turn a crank. If I release the brake, the bucket's going to fall. It's going to start with an initial velocity of equal to 0, and then it's going to have some final velocity down. It'll have some final velocity, but it'll spin my handle. So I can actually do this work. So it's kind of that interesting aspect of what we're calling work. We can look at it a little differently. Let's think about the fact that I've got a refrigerator or a box, and if I apply a force on the box and we get the box to move, right? And I move the box from here to here, I've done something that we actually call work. So I've applied a force, I've moved it a distance, and I've done something that we actually call work. So what we do here is we're going to define work as an interesting concept. It's a force, which is a vector quantity, and we're going to do what we call a dot product with another vector quantity, distance, and we're going to end up with a scalar quantity. So this kind of an interesting thought here. Work is a scalar quantity. It's also, if we remember it from chemistry, if you've had chemistry, we have this idea of a state function. And if we go back and think about what a state function is because we've dealt with this, if I have a mountaintop here and I'm going up my mountaintop and I start at the bottom and I go up to the top, we've had a change in height. And in order to do this state function, it doesn't matter whether I did this kind of a road. It doesn't matter if I did that or if I just went straight up. And that state function only cares about where we start and where we finish. It doesn't care if we went up the windy road. It doesn't care if we went up the short road. It just cares where we start and where we finish. So we have that idea of a state function. If we come back to our idea of work, okay, and we've now defined that as this dot product, and we want to look at this a little bit. So let's look if I have a little red wagon, and I have a handle on my red wagon, and I'm applying a force here to get my wagon to move, we have a problem. Because not all the force that I'm applying is going to actually give me motion in this direction. You guys saw that in your suitcase problem, because my force is actually got a force in the direction of the motion. And I have my force that's kind of referred to as a normal force. Now, this does us a little bit of good because like when the suitcase problem that you guys did for your homework, this counteracts friction. So it does me a little bit of good because now I'm not having to overcome that friction in order to get me to move. But I really want the best bang for my buck when I'm doing force over a distance is to be actually in line with my distance. I want my force being applied in the same direction that I want to move. And we're going to get the most work when I do that. And that's where this dot product comes in, that dot product. Because if I look at this example, my work that's being done is my force times the distance times the cosine of the angle, because that puts my force cosine of the angle is the force that is in line with the direction that I want to move. Okay, so the force cosines in direction that I want to move, the distance in there. So we can say work is force applied over a distance. Okay, work is force applied over a distance. So we can start looking at that and we can figure out how much work we've done. So let's talk about you've got a set of stairs here. All right. And we're going to do some work. And we're going to go up these stairs. Well, the distance that I go is going to equal the height. And we're going to say that this is 1 meter because we're going to say that that's my stoop. Well, the force that I have to apply to go up the 1 meter, all right, the force that I have to apply is going to be equal to the mass times gravity, or my weight. So the work that I do to go up the stairs is going to be the force times my height, which is going to give me my weight times my height. And that's the amount of work that I've done. So when you're working on that work laboratory, that's basically what you're doing. You're using your weight times the height. And if I put in my other variables, I get mgh. So work gets me there. So we can do our grocery cart problem. So I've got a grocery cart and I'm going to apply a force. All right, I'm going to apply a force And we're going to move my grocery cart 10 meters. And the force that I'm going to apply is 10 newtons, but I'm going to do it at an angle here. Oh, let's go ahead and say that that's 30 degrees. So I need the force that's in the direction. So that's going to be my force times the force in the direction is going to be in the x direction. It's going to be the magnitude is going to be the force there, cosine of the angle. So if I do 10 newtons cosine of 30 degrees, that's the force in my angle there. And that's going to give me 8.66 newtons. My force times my distance is going to equal the work. And the work is going to be 8.66 newtons times 10 meters. This is going to give me 86.6 Newton meters, but we're going to give this a new name. And our new name of Newton meters is going to equal a joule. And a joule is a unit of energy. So we've got a unit of energy. But one of the things that we see all of a sudden is I'm no longer, in order to do this calculation, I no longer have to worry about the directionality that we've been dealing with our vectors all this time. And things become really cool. So we can do a couple of different things. One is we can go back to our definition that work or that energy is the ability to do work. And we can go to our bucket problem here. So our bucket, let's give our bucket has a mass of 10 kilograms. And we're going to have our bucket fall 5 meters down the well. We know what our acceleration due to gravity is. Got gravity here. The work that we are going to do, or the work that this bucket is going to do, is going to equal our 10 kilograms. Our acceleration due to gravity, 9.81 meters per second squared. And we're going to drop it 5 meters. And so the work that's being done, because my cosine of my angle is equal to 1 in this case, because my force that's being applied and my direction are in the same direction, I don't have to account for that dot product now. I can do that. I can just do this right here. And so now I'm going to get my 10 times my 9.81 times my 5. And I'm going to do 490.5 joules of work. So we can actually look at that. That's pretty cool. But we're going to make a definition here. We're going to define this energy due to position as something that we're going to call potential energy. And you can think of this as if I have a ball and I'm going to lift it up to a height h here, I have to apply a force to overcome gravity. And now that once that ball is up there, I have stored the work as energy. So I had to overcome the weight to a height and store the work as energy. So we're going to define potential energy, which your book uses the letter U, as mgh. That's our potential energy of an object. And in chemistry, we've done lots of chemistry. We know that energy is conserved. We know that mass is conserved. And we're going to use this idea that energy is conserved to help us do a lot of problems. So energy is conserved. Energy is always in there. It's just going to change form. So I can do work to lift up my mouse to a height. I've done work, but now that I've put that work in there, the work that I've got up into the mouse is equal to its potential energy. And now I can drop the potential energy, or drop it, and it's going to move, and I can actually look at it. And when it's moving, we know that we have something called kinetic energy. And my kinetic energy is going to be defined as 1/2 mv squared, where v is our velocity. Okay, kinetic energy is mv squared. Now you can go back to your textbook and you can look at, in your textbook, you can look at the derivation of this. You can look at my pile driver problem, and I encourage you to look at the pile driver problem because that's going to give us what we call the work energy theorems. And the work energy theorems tell us how to work problems. Well, it allows us to work problems using our idea of conservation of energy. Okay, so let's look at dropping a ball. All right, so we've got our ball, we're going to drop it. Okay, we've got our acceleration due to gravity. We're going to start with an initial velocity is equal to 0. We know that my building height, we're going to give my building height as 11 meters. And we've been doing these problems now for a while. And we want to know what the final velocity is. Okay, well, we can do this. Remember that I have v final squared is equal to v initial squared minus 2, my acceleration due to gravity times my height, because that's my kinematics equation. So this equation is coming from kinematics. And we can say, all right, if I start with a 0, right? Well, my height is negative, so I get v final squared is equal to 2. I'm going to do my negative. I've got 9.81 meters per second squared, and I've got my negative 11 meters. And so now I got v final squared, or I've got this as the square root of 2gh is my v final. And we can get that calculation. So I got 2 times 9.81 times 11. So let's go ahead and do the calculation. And it says that we're going to end up at 14.7 meters per second. We've been doing that problem all along, but now let's look at it with our idea of conservation of energy. looking at using conservation of energy and do this same problem, but we're going to do it in the energy arena. So if I do this, and I still have my 11 meter building, I still have my ball here. And my ball has some mass to it. Okay, so we got some mass up here. Conservation of energy says that the total energy at the top has to equal the total energy at the bottom. I got my total energy at the top. It's got to equal my total energy at the bottom. But when I'm at the top, total energy is equal to potential energy. When I'm at the bottom, total energy is equal to kinetic energy. And we've defined potential energy as mgh. And we defined kinetic energy as 1/2 mv squared. All right. So if I look at potential energy at the top is going to equal my total energy, which is going to equal my kinetic energy at the bottom, I'm going to get mgh is equal to 1/2 mv squared. My masses cancel. I get 2gh is equal to v squared. The square root of 2gh is equal to v, which is the same result that we got from our kinematics. Now, we have conservation of energy. Now, over a 10 meter building or a short distance, that's absolutely totally true. And actually, this is totally true no matter what. But if I drop a ball and there's air, I'm going to get air resistance. Ew. What about air resistance? Air resistance is kind of like friction. If I'm on an inclined plane and I'm dropping the mouse along the way, ew, I've got friction. And we know about friction. Friction is going to generate heat. And once I generate that heat, trying to capture that heat becomes difficult. So when we deal with our work energy theorems, we have to think of our conservative forms of energy plus our non-conservative forms of energy. Okay. And what that means is if I take a hockey puck and I give it a tap, all right, I give it a tap, and we know it ultimately is going to stop. And we know ultimately at some distance it's going to stop. We know that the total energy at the beginning has to equal the total energy at the end. And what's happened is we've lost energy due to heat or friction. Okay, so we know that we can get that. So we can actually look at this non-conservative form of energy for a lot of problems, but a lot of problems like sliding down a slide. Okay, if I have a kiddo that weighs 45 kilograms, my slide is, we're going to do it as 1.5 meters up. We can calculate the work. The work has got to equal my 45 kilograms times gravity times the height. So I can do that. That gives me 661.5. I'm going to double check that. And this is in Newton meters or joules. Okay, I obviously did something weird. Let me get that numbers. I've got two different numbers. So 45 times 9.81 times 1.5. Okay, I got that number twice. So we're going to stick with that number, 600 joules. But now that's the work that we did to get up to the top of the ladder. But now the work is equal to the potential energy at the top. So we know that we've got 662.2 joules at the top. And at the bottom, we know we got 662.2 joules at the bottom. We can calculate the velocity. Okay, well, the velocity in this case is going to be the kinetic energy is equal to 1/2 mv squared. So I'm going to have 2 times the kinetic energy divided by the mass is going to equal my velocity squared. So velocity is going to equal 2 times 6.62.2 divided by 45. Take the square root of that. And that's going to give me 5.4 meters per second. And so let's go ahead and do our units here. Let's do the unit analysis. So we said that 2 times kinetic energy divided by mass is going to equal meters squared seconds squared, because that was equal to velocity squared. 2 times joules divided by kilograms. A joule is a Newton meter divided by kilograms. And then I get kilograms meters per second squared times meters divided by kilograms. Kilograms cancel, and I get meters squared seconds squared. So I've done everything correct, and I have gotten my units that are there. So we can do an awful lot with our work energy theorem. Couple other things that we want to look at. The potential energy of a spring is equal to 1/2 kx squared. And that's kind of an interesting idea, because if I do for my spring, let's look at a spring, and I look at a force divided by stretch. So here's my stretch. And I look at my force. Work is going to be the area under the curve. So we can actually use that to our advantage as well. So this is potential energy of a spring. We also have to define power, and power is equal to work over time, or it's equal to my energy over time. So when you guys are doing your problem that you're working on for your laboratory, where you're increasing, going from the bottom step to the other step, you need to follow what happens if my time gets shorter. Well, if time gets shorter, the power is going to increase, right? Because if I look at, so let's say to go up the stairs is going to take 600 joules of work. All right. And we said that, and we're going to define power as 600 divided by my time. So if I'm at 600 divided by 1 second, so these are going to be joules, seconds are going to equal power. All right. So at 1 second, I'm going to be at 600 joule seconds. And that we also define as a watt. So I'm going to be at 600 watts. Well, now if I do my power at, say, it takes me only a half a second to get up there, that's going to be 1200 watts. So as it becomes faster and faster to get up here, this number is going to get bigger and bigger, and ultimately it'll be infinity. So power is an interesting way to compare things. And power was actually done to compare how much work could be done in an hour, because we used to deal with power with ponies. So if you think about the energy use, when you look at energy use in kilowatt hours, we're looking at how much energy that we use in 1 hour. And that's coming from our idea of this power ratio that people have. Okay. So my recommendations are, you want to review the videos that are there. Look at the pile driver video, because I take a lot more time to go through and derive how we're going to use these work energy theorems to be able to calculate different things. So you want to review those videos. There are a number of problems that are out there, and if you have a problem that you want me to work, please, please, please email me, and we can actually work a few of them. But you have a lot of these problems, but these problems are a lot easier because I no longer have to worry about dealing with the energy or dealing with the vector aspect of work and energy. You're going to use conservation of energy. And basically it is that the total energy at the beginning has to equal the total energy at the end. And we have defined potential energy as mass times gravity times h. You usually use a U in the textbook. We've defined kinetic energy as 1/2 mv squared, and that will usually use a K. And then there's potential energy in a spring, which is 1/2 kx squared. And then you've got power, which is equal to the work divided by the time, or energy divided by time. And that should get you started on your homework problems, and we will work more problems tomorrow. But please let me know what problems that you guys are having.